Hello everyone. Today I am going to present and implement what I learned in my 14-day internship on EV-ADAS System Real-Time Electric Vehicle Dashboard. During this 14-day internship, we learned the fundamentals of embedded systems using the STM32 Blue Pill microcontroller. We worked on peripheral programming, simulated hardware using PiximLab, and finally developed an EV controller with an ADAS system. The tools used are STM32 Cube IDE, simulator is PiximLab, and Blue Pill board, and the controller is STM32F103C8P6. This slide shows the complete architecture of our project. First, the sensors collect data such as accelerator position, brake position, battery state or SOC, state of charge, motor temperature. Then the STM32 microcontroller processes this data and computes vehicle parameters such as speed, SOC, torque, acceleration using formula of inertia model. Ultrasonic sensors detect nearby obstacles for the ADAS system. It calculates the front distance, left distance, and right distance. Finally, all the processed information is transmitted through UART to a Python dashboard where it is displayed in real time. The STM32 belongs to the ARM family. ARM is advanced RISC machine and it is widely used in embedded systems, mobile devices, IoT, etc. And it designs CPU cores. Cortex-A, R, and M are the ARM processor files, and STM32 belongs to the Cortex-M family, which are widely used in embedded systems because they are low power, high performance, and cost effective. Cortex M0, M0 Plus, M3, M4, M7, these are Cortex M series. Then before implementing our project, we implemented small peripheral, or we can say small parts. So these are some peripherals which we implemented to learn how they work. So first we implemented the ADC, analog to digital converter, to read speed, brake, SOC, motor temperature, and we collect data from potentiometers because we are not implementing on hardware and therefore we don't have real-time data. So we collect the data or we simulate the data from the potentiometers. So these potentiometers provide analog voltages between 0 to 3.3 volts, but the microcontroller can only process digital values. Therefore, we use a 12-bit ADC, peripheral analog to digital converter, which converts analog values into digital values ranging from 0 to 4095. We connected 4 potentiometers to represent the accelerator pedal, brake pedal, battery or state of charge SOC, and motor temperature. And these potentiometers were connected to these pins respectively. And the converted values were then transmitted to the virtual terminal using UART, Universal Asynchronous Receiver Transmitter. This is the formula for converting the analog values into digital values. This V is the voltage, current voltage. It is between 0 to 3.3 and V reference is the 3.3 volt, and dividing them and then multiplying them by 4095 gives the digital value, and this function is used for reading the ADC value. Then we implemented the ultrasonic sensors. The ultrasonic sensors is used for obstacle detection. It contains a transmitter and a receiver. First, the trig pin is made high for 10 microseconds, which sends an ultrasonic wave. When the wave strikes an obstacle and it reflects back, it is received by the echo pin. And we can calculate the time by measuring the time duration, how long the echo pin was high. This time we used for calculating the distance. How far is our obstacle. We use this formula, distance is equal to speed into time, and we use timers for calculating exact time. So we also implemented timers in our ultrasonic sensors, and these are used to generate accurate delays and measure time intervals. In our project, the timer generated a 10 microsecond delay for ultrasonic sensor. It also measured how long the echo signal remained high by counting clock pulses, called timer ticks. First, the trick pin was high for 10 microseconds and the ultrasonic wave was transmitted. Then trick pin was made low and echo pin was made high as it reflected back the wave. And as the echo pin is high, timer starts counting. And then when the wave has ended, the echo pin is low. It is made low and the timer stops counting. And this timer and this time which the timer counted is used to calculate the distance using this formula. Time into speed of sound divided by 2. We divide by 2 to calculate the one-way distance. Then before working with sensors, we learned GPIO programming by blinking the LED every 1 second. We connected the LED to PC13. We configured PC13 as an output pin using STM32CubeMX and alternately set the pin high and low with a delay of 1 second using the HL delay function. Then finally, we started implementing our project. After learning all these peripherals, how they work, how they are implemented, we start building our project. And first, we implemented EV controller. The EV controller reads the accelerator, brake, battery SOC, and motor temperature using ADC, analog to digital converter, every 10 milliseconds. Based on these inputs, it calculates speed, torque, acceleration, SOC, the power draw over time, and it also calculates the regenerative braking. And it also calculates the range based on SOC, how far, based on the current battery, how far our vehicle can go. And it also supports the driving modes such as eco, normal, and sport. Then we implemented the ADAS engine. ADAS system uses 3 ultrasonic sensors to detect obstacles in the front, left, and right directions. It calculates time to collision, and it provides warning and critical alarms or alerts based on the distance and time to collision. Distance of obstacle. It also detects blind spots and enables parking assistance at low speeds. Then we also implemented a finite state machine because our system can only be in one state at a time and it can change its state when an event or condition occurs. And we use the fault manager because various faults occur in our vehicle, and to check which fault has occurred and to flag that fault, we use this fault manager. These are our vehicle states: parked, ready, driving, region, fault. This is regenerative braking. And these are the transitions. From parked, our vehicle can change its state to ready. And from ready, it can change to driving. From driving, it can change to region. And from any of these, it can enter the fault state also. From any of these, it can enter the fault state. And fault states are, let's say, our motor overheats. Motor temperature is high. Or the SOC range is very less. Or collision occurs. These are the fault states. And we check the fault, update the fault flag, and print the fault flag and blink yellow LED. We blink the yellow LED for faults. And we have alarms also: warning, critical, advisory, and none. These are the alarms. And finally, all EV and ADAS data are transmitted from the STM32 board to the Python dashboard using the UART protocol every 100 milliseconds. STM32 sends 2 lines of plain text every 100 milliseconds, and the Python reads it, parses it, and redraws the screen. It sends 2 lines. Line 1 is the EV data, which includes the speed, SOC, torque, temperature, range, acceleration, and brake. And the line 2 is the ADAS data: front distance, left distance, right distance, time to collision, blind spot detection, alarm, and fault. And the Python dashboard displays the data in real time. It displays the speed, bird's eye view, the temperature graph, alarms, etc. So this was all about our project, what we implemented and what we learned. Now we are implementing on Pixim Lab and STM32 and on Python dashboard also. Now I'm going to show what we implemented in our project. So this is the code. This is our project EV dash, and it has all the files. The .c files contain the implementation actual code, and the .h files contains declarations, macros, and definitions used by other files. So this is the main.c. It is the main program file where the execution starts. It initializes all the peripherals and calls all modules. And here we have included all the .h files here. And this is the main.h. It contains function declarations and definitions used by the main.c. This common.h, it stores common macros, structures, and definitions shared across the project. Then EV control.c, it implements the electric vehicle control logic, speed, brake, accelerator, motor temperature, SOC, etc. And this EV control.h, it contains the function declarations for the EV control module. Similarly, this ADAS.c, it implements the ADAS logic such as collision warning and safety measures. And ADAS.h, it contains the function declarations for the ADAS module. Then we have the ultrasonic.c, it contains the code interface with the code to interface with the ultrasonic sensor and calculate distance. And the ultrasonic.h, it contains the function declarations for the ultrasonic sensor module. Similarly, we have the fault C file. It detects system faults and updates the fault status. And we have the fault H also. It contains the function declarations for the fault detection module. Then UART.shell. We have, it handles UART communication and process user commands. And UART shell.h, it contains the function declarations for the UART shell module. So this is our code, and we build our project. So there are no errors. We built our project, and now we're implementing our project on Pixim Lab, Drupal board, and from here file we can load our binary file. Load binary file, and this is EV-pin. I've already loaded it. So these are the spare parts. These are the 4 potentiometers: acceleration pedal, brake pedal, SOC, and motor temperature. These are the 3 ultrasonic sensors for calculating the front distance, left distance, and right distance. And these are the LEDs. The red LED blinks for collision when a collision occurs. The blue LED blinks when there is left distance is lesser, where the obstacle is there in the left, and the green LED occurs when the obstacle is there on the right of our vehicle. And this is the virtual terminal. Here it shows the speed, SOC, torque, temperature, range, acceleration, brake, and front distance, left distance, right distance, time to collision, blind spot detection, alarm, and fault. Let's say if I decrease the front distance, so it will show the red LED, and the yellow LED is also showing. See here, collision 2. So collision 2 is the critical alarm for red LED, and sorry, the fault is 04. The 04 fault is when the collision occurs. So we blink yellow LED when any fault occurs, and we identify the fault with the fault number here. For example, the fault 1 is when the motor temperature overheats. Fault 2 is for low SOC and so on. And if I increase the front distance, it will go off. And if I decrease the right distance, let's say, yes, the green LED blinks. Here we can see fault is green LED is blinking. And if I increase it, alarm 1. Alarm 1. If I increase it, it will go. Alarm again, it became 0. So when I decrease the left distance, the blue LED is blinking. And the alarm is now again 1 because it is the blind spot detection. And if I again increase it, it will go off. So now we'll implement it. We'll see it in our Python dashboard. We'll implement the Python dashboard. So this is our Python dashboard. It shows the speed. This is the speed and this is the speed graph. It is the battery. It shows the battery and it shows the SOC. Sorry, range. With the current battery, how long our vehicle can go. It shows the torque, acceleration, brake, motor temperature, alarm, fault, signal, and it shows the bird's eye view. This is our vehicle and this is the front obstacle. Left and right, it isn't showing. Now it will show if I decrease the left distance. The blue LED is blinking and it is showing the alarm advisory. Increase it a little bit. The vehicle is showing and the alarm will go off. Alarm will go off, but the vehicle is nearby. And if I decrease the right distance, the green LED is blinking and again the alarm is advisory. If I increase it a little bit, the vehicle is nearby, but the alarm will go off. Alarm none. And if I increase the front distance, say, the red LED will, sorry, the red LED is blinking and alarm is critical. Time to collision, it also showing the time to collision. Alarm critical, fault 04. Let's increase it again. And see, our battery is draining slowly. But the speed is increasing. It is increasing because we have increased, applied the acceleration and brake is 0. If I apply the brake and if I decrease the acceleration and increase the brake, the battery will not discharge anymore because it is regenerative braking. See, the torque is negative, it is regenerative braking. Acceleration is 24 and brake is 70%. Okay. So our speed will decrease, it will take time to show. But the battery is not discharging anymore. But if I again decrease the brake, and if I increase the acceleration, again the battery will discharge. See, it is discharged. If I increase the motor temperature, see, it will again show a fault 01. Fault 01 is over temperature. When the motor temperature gets high, it is showing 105.0 degrees Celsius. Go off again. So this is all what we implemented in our 14-day internship. Thank you for watching.